Hello, science lovers and exploration enthusiasts. Today we will tell you an exciting and detailed story of discovery about the thin atmosphere of the moon. How does the moon's atmosphere form, and what drives this process? In this video, we'll explore how scientists are solving these questions, what their data mean, and the mystery of the moon's atmospheric dynamics. It's common to imagine the moon as a piece of rock orbiting the Earth with no atmosphere. However, despite its lack of breathable air, the moon has a thin and delicate atmosphere, its exosphere. This exosphere is the very thin layer of gas that rises from the moon's surface and escapes into space. But how is this atmosphere formed, and what replenishes it? Scientists have been puzzling over the existence of this thin atmosphere for many years and investigating what processes drive it. Here we are with the answers to these questions. New research shows that the moon's thin atmosphere is constantly being renewed and sustained by meteorites hitting the moon. According to the research team, the moon's atmosphere is largely preserved thanks to the impact vaporization phenomenon caused by this meteorite bombardment. We have conclusively established that meteorite impact evaporation is the dominant process that forms the lunar atmosphere, said Nicole Nye, leader of the research team from MIT, Massachusetts Institute of Technology. The moon is about 4.5 billion years old, and during that time its surface has been continuously exposed to meteor showers. This process means that the moon's exosphere is constantly being replenished by small collisions. The moon's pockmarked surface clearly shows that it has been constantly bombarded by meteorites throughout its 4.5 billion year history. Early on, the young solar system was quite violent and chaotic. Because of this, the moon often collided with large meteorites. Over time, the size of these collisions became smaller, and micrometeorites, particles smaller than a grain of sand, began to hit the lunar surface. NASA's LADEE mission, launched in 2013 to investigate the moon's thin atmosphere and its environmental impacts, highlighted two processes that renew the moon's exosphere: impact evaporation and ion sputtering. High-energy charged particles known as the solar wind hit the lunar surface, energizing atoms, which are then ejected into the exosphere. During the LADEE mission, scientists observed that atoms in the moon's atmosphere increased during meteor showers. This suggested that impact events have an impact on the exosphere. However, changes in the atmosphere were also observed when the moon was in shadow from the sun. This suggested that solar winds also played a role. So both processes were involved in the renewal of the moon's atmosphere. Nye and his team studied lunar soil samples, collected from NASA's Apollo missions, to determine the primary process that sustained the lunar atmosphere. These samples, brought back during the Apollo missions, are extremely valuable for understanding the chemical composition and history of the lunar surface. The researchers analyzed the isotope ratios of the elements potassium and rubidium in these samples. Light isotopes were predicted to remain in suspension in the moon's exosphere, while heavy isotopes would fall back to the lunar surface. Isotopes are variations of an element with different numbers of neutrons. Light isotopes of potassium and rubidium tend to remain in the exosphere, while heavy isotopes fall back to the surface. The processes of impact evaporation and ion sputtering affect the rates at which isotopes remain in the atmosphere or escape into space. During impact evaporation, most atoms remain in the atmosphere, while with ion sputtering, many atoms are ejected into space. The research team found that heavy isotopes of potassium and rubidium were in the majority. This indicated that impact vaporization was the dominant process that vaporized atoms and lifted them into the lunar atmosphere. They concluded that 70% of the lunar exosphere was formed by meteorite impacts and impact evaporation, and 30% by solar winds and ion sputtering. The research team analyzed data from lunar soil to determine the ratios of potassium and rubidium isotopes. These isotope ratios are critical for understanding which process is more dominant. The presence of more light isotopes in the atmosphere indicates that impact evaporation is dominant, while the return of heavy isotopes to the surface indicates that ion sputtering is more effective. By examining these isotope ratios, the research team determined that impact evaporation was the dominant process. This finding suggests that the lunar atmosphere is constantly being renewed and that meteorite impacts play an important role in this process. It also suggests that these processes may operate similarly on other planetary and lunar surfaces and could be the focus of future missions. The researchers worked with very small samples to determine the ratios of elements and isotopes in the moon's exosphere. These samples weighed only 100 milligrams, as small as a drop of rainwater. Even these tiny samples provided critical information for understanding the moon's atmospheric processes. The moon's pitted and scarred surface clearly shows that it has been continuously bombarded by meteorites throughout its 4.5 billion-year history. Early on, the young solar system was highly violent and chaotic. Because of this, the moon often collided with large meteorites. Over time, the size of these collisions became smaller, and micrometeorites, particles smaller than a grain of sand, began to hit the lunar surface. These processes ensured that the moon's atmosphere was constantly replenished. The early solar system was a period of frequent large collisions and high-energy events. During this period, the moon and other planets often experienced large meteorite collisions. These large collisions shaped the surfaces of planets and moons and affected their atmospheric dynamics. The moon's surface also bears the scars of these great collisions. The processes of formation and renewal of the moon's atmosphere could work in a similar way on other bodies in the solar system. This provides an important clue for understanding the atmospheres of other planets and moons. Future missions could use this information to better understand these processes and unravel the history of our solar system more clearly. Nicole Nee and her team emphasized that these discoveries were possible thanks to the Apollo program. Without these Apollo samples, we would not have gotten precise data and detailed insights, said Nia. Bringing back samples from the moon and other planetary bodies is important so that we can more clearly chart the formation and evolution of the solar system. Knowing that the lunar atmosphere is renewed in this way not only helps us understand the history of the moon, but also the atmospheric processes of other planetary bodies. What do you think about these fascinating discoveries? Were you surprised to know that the moon's atmosphere is constantly renewed? Share your thoughts with us in the comments and subscribe to our channel so you don't miss out on other exciting developments in the world of science. See you in our next video.